In the 2002 National Electrical Code, NEC, the requirements for neutral bonding in alternating current AC systems are addressed in section 250.4. This section outlines the rules for connecting the neutral conductor to ground, ensuring a low impedance path for fault current to return to the source. The purpose of this bonding is to facilitate the operation of overcurrent protection devices, such as circuit breakers and fuses, in the event of a ground fault. This is a crucial aspect of electrical safety, helping to minimize the risk of electrical shock and fire. Grounding electrode conductor bonding for alternating current systems is covered in section 250.5 of the 2002 NEC. This section specifies the requirements for connecting the grounding electrode conductor to the grounding electrode system. The grounding electrode system typically includes items like ground rods, ground rings, or metal water pipes that are in direct contact with the earth for at least 10 feet. The grounding electrode conductor provides a path for fault current to flow to earth, helping to stabilize the system voltage and provide a reference point for electrical potential. Proper bonding of the grounding electrode conductor is essential for ensuring the effectiveness of the grounding system. Section 250.61b of the 2002 NEC addresses the grounding requirements for transfer switches. Transfer switches are used to switch between different power sources, such as utility power and generator power. This section specifically focuses on the grounding of transfer switches in systems where the transfer switch is used with a separately derived system like a generator. It mandates that the neutral conductor must be switched. It also stipulates how grounding connections should be made to ensure that the grounding system remains effective during the transfer between power sources. The proper grounding of transfer switches is critical for maintaining electrical safety and preventing equipment damage during power outages or other emergencies. When dealing with neutral bonding, it's important to understand the concept of a separately derived system versus a non-separately derived system. A separately derived system, such as a generator, has its own neutral conductor that is isolated from the building's main neutral conductor. In these systems, the neutral conductor must be bonded to ground at the source of the separately derived system. In contrast, a non-separately derived system does not have its own isolated neutral conductor, and the neutral conductor is already bonded to ground at the main service entrance. In these systems, it is important to avoid creating multiple neutral to ground bonds, as this can cause circulating currents and other problems. Grounding electrode conductor installation requirements are specified in 250.62, which mandates that the grounding electrode conductor be securely fastened to the surface on which it is carried. A metal enclosure containing a grounding electrode conductor shall be electrically continuous from the point of attachment to cabinets or equipment or to the grounding electrode and shall be securely fastened to the ground clamp or fitting. Metal enclosures shall be protected from physical damage where necessary. The size of the grounding electrode conductor is also determined by 250.66, which indicates the sizes based on the size of the ungrounded conductors. For example, if the ungrounded conductors are 1100 copper or 1750 aluminum, the grounding electrode conductor should be at least number 3 copper or 1/0 aluminum. If the ungrounded conductors are 3/0 copper or 500 aluminum, the grounding electrode conductor should be at least number 1/0 copper or 3/0 aluminum. For systems using a grounded conductor, the grounding electrode conductor connection should be made at an accessible location on the following one of the grounded conductor, the supply side of the disconnecting means, or the equipment grounding conductor of the disconnecting means. Grounding requirements for separately derived alternating current systems are found in 250.30. Separately derived systems are electrical power sources, such as generators or transformers, that derive their power independently from the main building electrical system. These systems require specific grounding configurations to ensure electrical safety and proper operation. The grounding electrode conductor for a separately derived system must be connected to the system's grounded conductor, typically the neutral, at the source of the derived system. This connection establishes a low impedance path for fault currents, facilitating the operation of overcurrent protection devices. The size of the grounding electrode conductor must be determined based on the size of the derived system's conductors, as specified in NEC Table 250.66. The grounding electrode must be as near as practicable to, and preferably in the same area as, the separately derived system grounding connection. This proximity minimizes impedance and ensures effective grounding. The grounding electrode must consist of one or more of the electrodes specified in 250.52. These electrodes include metal underground water pipes, metal frames of buildings or structures, concrete encase electrodes, ground rings, and rod and pipe electrodes. The selection of the appropriate grounding electrode depends on site conditions and local requirements. It is important to note that the NEC outlines specific requirements for each type of grounding electrode, including minimum size, installation depth, and bonding methods. Grounding requirements for equipment are detailed in 250.110. Exposed metal parts of electrical equipment that are likely to become energized must be grounded. This requirement applies to a wide range of equipment, including enclosures, raceways, and electrical appliances. The purpose of equipment grounding is to provide a low impedance path for fault current to flow back to the source, tripping over current protection devices and preventing electrical shock hazards. Equipment grounding can be achieved by connecting the metal parts of equipment to the grounding electrode system through an equipment grounding conductor. The equipment grounding conductor must be sized in accordance with NEC Table 250.122, which bases the conductor size on the rating of the overcurrent protection device protecting the circuit. It is important to ensure that all equipment grounding connections are secure and reliable. Loose or corroded connections can increase impedance and reduce the effectiveness of the grounding system. Grounding of electrical systems is a critical aspect of electrical safety and must be performed in accordance with the requirements of the National Electrical Code. Proper grounding protects people from electrical shock hazards, minimizes the risk of fire, and ensures the proper operation of electrical equipment. Bonding of electrical equipment and enclosures is addressed in 250.92. Metal enclosures, raceways, and other non-current carrying metal parts of electrical systems must be bonded together to form a continuous electrical path. This bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of electrical shock. Bonding can be achieved by using bonding jumpers, bonding screws, or other approved methods. The size of bonding jumpers must be determined based on the size of the circuit conductors, as specified in NEC Table 250.102. It is important to ensure that all bonding connections are secure and reliable. Loose or corroded connections can increase impedance and reduce the effectiveness of the bonding system. The neutral conductor is typically insulated and carries the return current from electrical loads back to the source. The equipment grounding conductor is typically bare or green insulated and provides a low impedance path for fault current to flow back to the source. The grounding electrode conductor connects the grounding electrode system to the electrical system, providing a path for fault current to flow to earth. Neutral to case voltage can indicate problems with the grounding system, such as loose connections or imbalanced loads. High neutral to case voltage can create electrical shock hazards and interfere with the operation of sensitive electronic equipment. Ground loops can occur when there are multiple ground paths in an electrical system. Ground loops can cause circulating currents, which can create noise and interference in electronic equipment. Ground loops can be prevented by ensuring that there is only one path for ground current to flow. This can be achieved by using isolated grounding receptacles and avoiding multiple neutral to ground bonds. Effective grounding practices include verifying that all grounding connections are secure and reliable, inspecting grounding conductors for damage or corrosion, testing the grounding system to ensure that it is functioning properly, following the requirements of the National Electrical Code, consulting with a qualified electrician if you have any questions or concerns about grounding. The purpose of this is to ensure that electrical systems are properly grounded to protect people from electrical shock hazards, minimize the risk of fire, and ensure the proper operation of electrical equipment. The NEC contains detailed requirements for grounding electrical systems. Adhering to these requirements is essential for ensuring electrical safety. Understanding the function of each component of the grounding system is essential for ensuring that the system is properly installed and maintained. Grounding is a critical aspect of electrical safety and must be performed in accordance with the requirements of the National Electrical Code. Proper grounding protects people from electrical shock hazards, minimizes the risk of fire, and ensures the proper operation of electrical equipment. Understanding the difference between a separately derived system and a non-separately derived system is crucial for proper grounding. Separately derived systems, such as generators, require specific grounding configurations to ensure electrical safety. Avoid creating multiple neutral-to-ground bonds in non-separately derived systems, as this can cause circulating currents and other problems. Ensure that all equipment grounding connections are secure and reliable. Loose or corroded connections can increase impedance and reduce the effectiveness of the grounding system. Bonding metal enclosures, raceways, and other non-current carrying metal parts of electrical systems is essential for minimizing the risk of electrical shock. Neutral to case voltage can indicate problems with the grounding system. Investigate and correct any high neutral to case voltage readings. Avoid ground loops by ensuring that there is only one path for ground current to flow. Regularly inspect and test the grounding system to ensure that it is functioning properly. Consult with a qualified electrician if you have any questions or concerns about grounding. By following these grounding practices, you can help to ensure the safety of electrical systems and protect people from electrical hazards. It is always recommended to consult the latest edition of the NEC and SEC guidance from qualified electrical professionals for specific grounding requirements and best practices. The information provided here is intended for educational purposes and should not be considered a substitute for professional electrical advice. Understanding the principles of grounding and bonding is paramount for ensuring electrical safety and compliance with the National Electrical Code. By following the guidelines outlined in the NEC and consulting with qualified professionals, you can help create a safe and reliable electrical system.